As professional pilots, we spend a lot of time doing cross-checks. These are based on our knowledge of how our aircraft works combined with our understanding of human error. Cross-checking of the aircraft and ourselves is designed to trap errors and prevent them creating a problem for either ourselves or our passengers. I guess it is fair to say that the only two things we have really learnt to trust are the windsock and the ILS.
The level of trust that pilots and aircraft designers have in the ILS system is shown by the fact that in low visibility we routinely fly down to 200 feet and in some cases conduct auto-land approaches right to touchdown. We believe that as long as the autopilot is coupled to the aircraft, we have no warning flags and there is a valid ident signal from the approach aid, we can conduct a safe auto-land approach. But it is not that simple. To help us understand, let's go back to the night of the 29th of July in 2000. Around midnight, flight NZ60 was en route from Auckland to Apia. During their pre-flight briefing, they discussed all the NOTAMs regarding the degraded state of the aids at Apia. The Faliolo VOR, the ILS DME and glide path for runway 08 were all unmonitored. To join finals for runway 08. It was a dark, moonless night and the controller at Apia was reporting scattered cloud over the airfield. As an extra precaution, they briefed for the VOR DME approach to runway 08 in case the ILS was not functioning. In a moment, we'll let the crew help tell you the story as they made their approach for runway 08.
As we came around the arc, everything was fine. But suddenly, at Glideslope intercept, everything became rushed. The aircraft pitched down, but now the aircraft was a lot faster than you should be as you commence the descent for the ILS.
The glideslope capture happened almost immediately after the approach mode was selected. The captain had the aircraft in vertical speed mode to slow down and was concerned that the aircraft seemed to accelerate as it pitched down with the glideslope capture. But the ILS indications were all correct, so the captain concentrated on managing the energy problem.
I reconciled it by saying tailwind, heavy weight.
There were no flags, no warnings of any sort to indicate that there was anything other than an autopilot capture of a valid localizer and a valid glide slope. If we were getting preoccupied with managing the aeroplane and slowing down and configuring.
At 1,000 feet, the crew had completed the landing checklist. Each started to think again about the unease they had felt when the aircraft had captured the glide slope so quickly.
Why were we rushing? Why was the aeroplane going down so quick? Why were we needing to use speed brake? Why were we needing to use the gear?
I was heads down managing the aircraft all the way through till the landing checklist was complete.
With the aircraft now set up for landing, they started to revisit their doubts. They were looking for something to confirm that the on-slope glide slope indications were, in fact, correct.
Looked up to clarify in my own mind where we were. Something in my mind said things were not right.
All three pilots looked up through the forward windscreens, expecting to now see the runway lights in front of them. The captain reported seeing a mishmash of lights and thought that scattered cloud, previously reported by Apia Tower, might be partially obscuring them. The other pilots could not see the runway lights either.
Well, when I looked out the windscreen and I couldn't see the airfield and I expected to.
I remember looking up the windscreen and all I could remember seeing is two dim red lights. I thought, oh, that's interesting. Where's the airport? It didn't make any sense to me, so I came back inside. I saw that the glide slope and the localizer are both still centred. There are no warning flags, and the three autopilots are still engaged.
The first officer looked out of his side window and was surprised to see that the lights from the village on the adjacent island were so close. He voiced his surprise.
Well, shit, those lights are close.
At the same time, the captain was doing a DME cross-check, but was unable to make the answer tie up with the aircraft altitude.
I did the first DME check. It didn't make sense. What had I done wrong? And suddenly it all clicked that my DME checks were saying we weren't where we were supposed to be, and almost instantaneously all three of us said, go around, go around.
Go around, go around.
The autopilots were disconnected, and a missed approach was conducted to a safe altitude using only the standby instruments. The captain chose to fly to a safe position to assess what should be done next.
Once we'd levelled off at 4,000 feet, I was very keen for the captain to put the autopilot in, and I prompted him, but I was keen to for him to offload himself, and in doing so offload all of us a bit so we could ascertain exactly what we were going to do and use the autopilot to help join the arc and fly a second approach.
Restoring their confidence in the aircraft systems was not easy, and all three pilots discussed their situation carefully. Their discussion led them to suspect that the glide slope for a runway 08 was giving false information and could not be trusted. They then planned and executed a second approach, using the localizer and ignoring the on-glide path indication.
Let's look first at the technical aspects of the investigation, and specifically the ILS ground system. A basic ILS system provides horizontal and vertical guidance information to an aircraft. An ILS has 5 distinct components. These are the localizer transmission system, the glide slope transmission system, co-sighted distance information from a DME or a marker system, a second standby transmitter, and a remote control and indicator system. The Morse code identifier signal, or ident, is carried on the localizer carrier signal only. The ramifications of this are not widely appreciated. An audible and valid ident is, therefore, only guaranteeing you that the localizer carrier signal is transmitting. It does not ensure that the glide slope is transmitting. 2 separate transmitters generate the localizer and glide slope signals. Each transmitter receives signals from a pair of amplifiers. Historically, we've been led to understand that both the electronic localizer and glide slope signals form narrow, tightly focused beams which the aircraft receiver sensed. The actual signal pattern is, as you will see, rather different. The 2 glide slope amplifiers provide signals to the glide slope transmitter. The transmitter then routes the signals to 2 independent aerials. The 2 aerials that create the total glide path signal are located on a tower near the runway and abeam the touchdown point. The lower aerial radiates the carrier wave. This carrier is formed by a UHF signal and is modulated or adjusted with 2 other frequencies of 90 Hz and 150 Hz. The resulting signal contains equal amplitude 90 and 150 Hz modulations. This carrier wave on its own does not provide any glide path guidance. The upper aerial radiates 90 Hz and 150 Hz modulations only. These signals are transmitted in a specific phase relationship, with the 90 Hz and 150 Hz signals being transmitted by the lower aerial. As a result, a complex interference pattern is formed, effectively creating upper and lower side lobes as shown in the diagram. The null between the 90 and 150 Hz side lobes define the glide slope. If the aircraft is below the desired 3-degree glide path, it will sense a predominance of 150 Hz. If it is on the desired glide slope, it will sense the null between the 90 and 150 Hz signals, so that the flight instruments will show on slope. If it is above the desired 3-degree glide path, it will sense a predominance of 90 Hz. This is the normal operation of the glide slope transmitter. Let's look at the abnormal ILS glide slope transmission that occurred on the night. The glide slope side lobe amplifier was not operating, so the aircraft only received the glide slope carrier wave. Because the carrier signal has equal amplitude 90 and 150 Hz modulations, this signal was electronically interpreted as being on glide slope. As a result, NZ60 only ever received the carrier wave transmission for the glide slope, and so the aircraft always sensed that it was on slope. As the carrier signal was being received, the aircraft instrument glide slope warning flags consequently were removed from view. The erroneous glide slope will show that you are on slope regardless of your approach slope or where you intercepted it. You will have no flags, have an on-slope indication and a normal ident. In addition, your sink rate could look quite reasonable. Even a GPWS would not prevent an accident in this case. The alerts are inhibited if the rate of closure with the ground is within design parameters, and especially if the aircraft is configured for landing, even though the touchdown point might be several kilometres from the runway. However, aircraft fitted with a terrain awareness warning system, for example EGPWS, would receive an alert in this situation.